Okay, so this next section is on the other trigonometric function. So we talked about sine and cosine of any angle. Now we want to talk about the other trig functions, tangent, cosecant, secant, and cotangent. So this is section 5.4. Let me go to black. So 5.4. The other trigonometric functions. Okay, so again, this is going to be true for any angle, but I'm just going to draw it so that it's in the first quadrant, but it can be any quadrant. Okay, so let's say we have, right, here's our point, this is R, again, this point is going to be X, comma, Y. So that means that this distance is really the Y value, and then this distance would be the X value. And we already know, and this of course is the angle theta right here. And we already know that the definition for sine of theta, it's going to be Y divided by R, and cosine of theta is X divided by R. And then the other trig functions, so tangent, and you guys could probably figure this out from our right triangle, right? Since I'm in the first quadrant, remember you can think of right triangle trig. So remember TOA, tangent, is opposite over adjacent. So that would be Y, right, opposite over X. But again, this is going to be true for any quadrant now. Cosecant, which I write as CSC of theta, that is equal to R over Y. We're going to see later it's just the inverse of sine, right? So it's the sine when flipped. And then secant is just the inverse of cosine, so this is going to be R over X. And then cotangent, so COT is cotangent, that's going to be the inverse of tangent, so that's going to be X over Y. Okay, so again, the other ones were, I'll write them out here in terms of the names. So we had tangent, right, that's tan. Secant, so SEC. Cosecant is CSC, and then cotangent, which is COT. All right. Now the nice thing, and I just sort of explained this here, but let me write this out formally, is that those new four trig functions, tangent, cosecant, secant, and cotangent, can be related back to the sine and cosine functions. Okay, so I'll write that out here. So these new trig functions can be related back to the sine and cosine functions. Okay, how are they related? Well, it turns out that tangent of theta is the same, it's defined to be the sine of theta divided by the cosine of theta. Cosecant of theta turns out to be 1 divided by the sine. So it's the inverse of the sine, right? Or 1 divided by the sine. Secant of theta is 1 divided by cosine. So that you just have to remember. The way I kind of remember it is cosecant and secant are kind of backwards. Like cosecant, the c corresponds to sine s, so it's 1 over sine, and secant corresponds to cosine, the c, right? And then cotangent of theta is really 1 over tangent. But remember, since tangent is sine over cosine, this is going to flip it. This is going to be cosine of theta divided by sine of theta. Okay? And these relations here are called identities, right? Identities are statements that are true for all values of the input on which they are defined. So these are just identities. Everything relates back to sine and cosine. Okay, so let's do some examples of this. Let's say I'm given the following. Let's say if theta equals pi over 4, right, meaning pi over 4 radians, find exact values for, let's say, all 6 of our trig functions. So sine of theta, cosine of theta, tan of theta, and then cosecant, secant, and cotangent. Right, so we want to find exact values for all of those. So first of all, let's figure out sine and cosine. That we can get just by, we learned that in the previous section, right? So pi over 4 would be in the first quadrant. So the reference angle is the exact angle, right? That it's the same because it's in the first quadrant. And remember, if you want that in degrees, this is 45 degrees. Okay. So we know that sine of 45, or sine of pi over 4, is radical 2 over 2, right? So that's given, or that we know from the previous chapter. Cosine of pi over 4 is also radical 2 over 2. You can either remember those values, right, those special angles. You could look at the trigonometry wheel, or you could draw like a quick little 45, 45, 90 right triangle, and you could get those particular values. Okay. Now, how do we get the remaining 4 trig function values when they're evaluated at pi over 4? We just use the fact that everything's related back to sine and cosine, right? So if I want to know tangent of pi over 4, well, that's going to be, by definition, sine of pi over 4 divided by cosine of pi over 4. So in this case, this is radical 2 over 2 divided by radical 2 over 2. If you want, there's a couple ways you can think about this, right? You can say, well, anything divided by itself is equal to 1. Or if you actually want to divide these fractions, it's the top fraction times, you multiply by the reciprocal of the bottom one, right? The reciprocal of the divisor. And of course, you're going to get 1, right? In either case, you're going to get 1. So tangent of pi over 4 is equal to 1. What was the next one? Cosecant. Well, remember, cosecant of pi over 4, by definition, that's 1 over sine of pi over 4. And we just said sine of pi over 4 was radical 2 over 2. So this is 1 divided by radical 2 over 2. Again, if you want to think about this as dividing fractions, think of the 1 as 1 over 1 divided by radical 2 over 2. So this is 1 over 1 times the reciprocal. So this is just going to be 2 divided by radical 2. But then often people want to rationalize the denominator. So to do that, I'm going to need to multiply the numerator and denominator by radical 2. Rationalizing the denominator means remove the denominator, or remove the radical from the denominator. So if I do this, this is going to be 2 radical 2. And then radical 2 times radical 2 is 2, right? It's radical 4 or 2. And then these cancel, so this is just radical 2. So cosecant of pi over 4 is simply equal to radical 2. Then I want to do what? Secant. Well, by definition, secant is going to be 1 over cosine. But in this case, that's the same, right? It's 1 over radical 2 over 2, because cosine of pi over 4 is the same as sine of pi over 4. So when you work this out, you're going to get the same thing. This is just equal to radical 2. And then finally, what was the last one? Cotangent. So this is 1 over tangent of pi over 4. But we already did tangent, right? Tangent of pi over 4 is equal to 1. And then 1 divided by 1 is also 1. So it turns out that cotangent of pi over 4 is also equal to 1. Okay, so we find sine and cosine first, and then we use the fact that all the other trig functions can be related back to sine and cosine to figure out all those particular values. Okay, here's another example. Let's say we're given that the angle is 2 pi over 3. So if theta is equal to 2 pi over 3, then we want to find exact values for, I'll just say, all 6 trig functions. Okay, so start by finding sine and cosine, right? So again, I would draw a little picture. Where's 2 pi over 3? Well, 3 pi over 3 would be 180 degrees. So that would be pi. So I guess 2 pi over 3 would be somewhere in the second quadrant, like this. And in fact, so this angle would be 2 pi over 3. And then if I want the reference angle, that's going to be pi minus 2 pi over 3. So that's just going to be pi over 3. Right? So the reference angle is equal to, I did pi minus 2 pi over 3. Well, that's just pi over 3, which, by the way, is 60 degrees, right? If you want to know the angle in degrees. So this is 60 degrees, the reference angle. Okay. So remember that sine of 2 pi over 3 and cosine of 2 pi over 3 are going to be the same as sine of pi over 3 and cosine of pi over 3, except they may differ by an SIGN, right? A sign, whether positive or negative. So what is sine of pi over 3? Well, again, you can either memorize this, right? Remember sine of 60 or cosine of 60, or you could draw a quick little picture. I'll draw my 30, 60, 90 right triangle, draw it this way. So if this is 60, this is 30, right? Remember it's 1, 2, and then the long leg is radical 3. So sine is opposite over hypotenuse. So this would be radical 3 over 2. And cosine is adjacent over hypotenuse. So it would be 1/2. And then if we want sine of 2 pi over 3, cosine of 2 pi over 3, these are going to be the same, except we just have to check on the SIGN. Well, remember, we're in the second quadrant. So what is positive in the second quadrant? Well, remember, it's all students, so sine, take calculus. So sine is positive, cosine and tangent are negative, right? So sine is positive, so that's radical 3 over 2, but the cosine should be negative. Or the other way you can think about it is in the second quadrant, the x coordinate is negative, the y is positive. So again, that's going to make cosine negative and the sine positive. Great. Now that we have that, we can figure out all the other trig functions, right? So I know that I'll start with tangent. By definition, it's sine divided by cosine. So it would be radical 3 over 2 divided by minus 1/2. So if I want to divide fractions, I'll take the first fraction that stays the same. I'll multiply by the reciprocal of the second. Notice how the 2's cancel, and I'm going to get negative radical 3. So it looks like tangent of 2 pi over 3 is negative radical 3. Okay, then cosecant. Remember, by definition, that's 1 over sine of 2 pi over 2/3 pi, or 2 pi over 3. Well, what was sine of 2 pi over 3? That was radical 3 over 2. So if I can think of this as 1 over 1, right, divided by radical 3 over 2. So this is 1 over 1 times the reciprocal. So this would be 2 over radical 3. But then often you're going to want to rationalize the denominator. So that means getting that radical out of the denominator. So to do that, I can multiply by radical 3 over radical 3. And that's going to give me 2 radical 3 over 3. Right? And it's positive in this case. In fact, in that second quadrant, the sine, S is positive, right? All students, sine is positive. And the inverse, 1 over sine, also has to be positive. So cosecant is also positive. Everything else is negative. Okay, so next was secant. Well, remember that's 1 over cosine. But cosine was negative 1/2. So what's 1 divided by negative 1/2? Well, again, I could write this as 1 over 1 times, and then flip the second one. So this is just negative 2. And then finally, the last trig function is cotangent. Well, that's 1 over tangent. Or if you want, you could say, since tangent is sine over cosine, this is going to be the reverse. It'll be cosine divided by sine. Either way, or you can just directly do 1 over tangent. So this is going to be, I'll just use cosine divided by sine. So this would be negative 1/2 divided by, and then sine was radical 3 over 2, right? So now this is going to be negative 1/2 times 2 over radical 3. 2's cancel, and I get negative 1 over radical 3. But again, if we want to rationalize the denominator, I'll multiply by radical 3 over radical 3. So this, I guess, is negative radical 3 over 3. So that would be the cotangent of 2/3 pi. Okay, so really the whole thing stems on figuring out what sine and cosine are first. That's the key thing. And then you can get all the other ones from sine and cosine. Let's do another one. Let's say in this question you're told if cosine of theta is equal to negative 1/3, and theta is in quadrant 3, okay, so cosine of the angle is negative 1/3, and the angle is in quadrant 3. We want to find the remaining 5 trig functions, right? So I want to find sine of theta. I want to find secant of theta. I want to find cosecant of theta, tan theta, and so on. Tan theta, and then what else? Cotangent, right, of theta. Okay, so again, there's many ways you could do this, right? We're given one of the 6, right? We know cosine of theta is negative 1/3. We could find sine of theta using the Pythagorean identity. That's one way of doing it. Actually, let's do it that way just for practice. So remember, Pythagorean identity says cosine squared of theta plus sine squared of theta equals 1. And I already know that cosine of theta is negative 1/3. So this is like saying negative 1/3 squared plus sine squared of theta is equal to 1. So this is like 1/9, right? Positive 1/9 plus sine squared of theta is equal to 1. If I subtract 1/9, I'm going to get, I'll finish it up over here. Sine squared of theta is equal to 1 minus 1/9. Well, what's 1 minus 1/9? It's 9/9 minus 1/9. So this is going to be 8/9, right? And then if I want to get sine by itself, I need to take the square root of both sides. And I have to allow for the possibility it could be positive or negative. So sine of theta is going to be plus or minus, I'll write it as the square root of 8 over the square root of 9. But it turns out 8 I can write as 4 times 2. So I could pull out, right, a 2, and I'm left with a radical 2 inside. So square root of 8 is 2 radical 2. And then square root of 9 is just 3. Okay? But the question is, which one do I use? Do I use the positive or negative? Well, we're told that we're in the 3rd quadrant, right? Theta is in the quadrant 3, 3rd quadrant. So in the 3rd quadrant, all students take tangent is positive, but sine and cosine must be negative, right? Tangent's positive, so sine and cosine are negative. Or the other way to think about it, in the 3rd quadrant, my x and y values are both negative, right? So y over r has got to be negative. So I know that sine of theta is going to be negative 2 radical 2 over 3. Right? I was given cosine. Let me just write it down here. So remember, cosine of theta was negative 1/3. And I just figured out that sine is negative 2 radical 2 over 3. But now that I have those two, I can figure out all the other ones, right? So let's do tangent. Tan of theta must be sine of theta divided by cosine of theta, right, by definition. So this is negative 2 radical 2 over 3 divided by negative 1/3. Well, that's the same as negative 2 radical 2 over 3 times negative 3 over 1. 3's are going to cancel. Negative times negative is positive. And I'm just going to get, I guess, 2 radical 2. So it looks like tan of theta is going to be 2 radical 2. Now, let's do cosecant. So cosecant of theta is 1 over sine. So this would be 1 over negative 2 radical 2 over 3. Well, that's the same as 1 over 1 times the reciprocal. So this would be negative 3 over 2 radical 2. And then probably what you would do is, again, clear out the radicals from the denominator, so rationalize the denominator. So I could do that if I multiply by radical 2 over radical 2. Then this becomes negative 3 radical 2. And on the bottom, I'm going to have 2, and then radical 2 times radical 2 is another 2, so this is going to be 4. So I guess it's cosecant of theta is negative 3 radical 2 over 4. Then what do I have left? I have secant of theta. Well, that's 1 over cosine. And then cosine was, what was cosine? Cosine was negative 1/3, right? So that's just 1 over 1 times the reciprocal, and that's just going to be negative 3. So secant is negative 3. And then finally, cotangent is, I can either say it's cosine over sine, or it's just 1 over tangent. Let me just write it as 1 over tangent in this case. So 1 over tangent. And tangent we found was 2 radical 2. But then I want to rationalize the denominator again. So I'll multiply this by radical 2 over radical 2. And now 1 times radical 2 is radical 2. And then denominator I have 2, radical 2 times radical 2. So that's 2 times 2, which is 4. So that would be the cotangent of the angle. Okay, so we don't even need to know the exact angle, right? We just did this in general, just by knowing to start with that we had, right? We don't need to know that angle. We could figure it out using inverse functions, but we weren't asked that. Given the fact that cosine of theta is negative 1/3 and theta is in the third quadrant, we are able to figure out sine of the angle, tangent of the angle, secant, cosecant, and cotangent. Right, we're able to figure out all the other 5 functions. Okay, there's a few, I probably won't use these 2 identities too much, but let me just mention there's a few other identities that basically come from the Pythagorean identity. So let me just mention those. So I'll just say more trigonometric identities. Should really do a capital T there. And these really come from the Pythagorean identity. So we're going to derive them starting with the Pythagorean identity. So remember what that is. So we're going to start with cosine squared of theta plus sine squared of theta is equal to 1, right? That's the Pythagorean identity. And let's divide both sides by, let's say, cosine squared of theta. Okay, so I'm going to divide the left-hand side by cosine squared of theta, and the right-hand side by cosine squared of theta. Well, if you look at this left-hand side, right, I can split this up. This is really the same as cosine squared of theta divided by cosine squared of theta plus sine squared of theta divided by cosine squared of theta equals 1 over cosine squared of theta. If you want, right, you can further break this down. Well, first of all, cosine squared over cosine squared, right, these are going to cancel. This is just 1. You can think of this as sine of theta over cosine of theta all squared. And I can think of this as 1 over cosine of theta all squared, right? It's like the square of a quotient is going to be the quotient, is going to be the numerator squared divided by the denominator squared, if I square the quotient. And then, but what is sine over cosine? Sine over cosine is tan, right? So this is 1 plus tangent squared of theta. That equals, and remember 1 over cosine is secant. So this is going to be secant squared of theta. So just by dividing by cosine squared of theta, starting with the Pythagorean theorem, dividing by that, I've gotten a new identity here. The fact that 1 plus tan squared of theta equals secant squared of theta. And then I could do the same thing. So now I want to divide by sine squared. So I'm going to start with my Pythagorean identity. And now I want to divide by sine squared instead of cosine squared. So sine squared of theta. And what's going to happen in this case is I'm going to get cosine squared of theta over sine squared of theta plus sine squared of theta over itself equals 1 over sine squared of theta. But what's cosine over sine? That's cotangent, right? So really this first term is like cotangent squared of theta. Sine squared theta over sine squared theta is 1. And remember, 1 over sine is cosecant, so the right-hand side is really cosecant squared of theta. So we have another identity. Again, it's nothing more than starting with the Pythagorean identity and dividing both sides by sine squared. So all of these are really related to the Pythagorean identity. And sometimes they come in handy. Okay, there's one more thing I want to do. I want to simplify expressions involving trig functions, and then this is sort of related, and prove identities. Like prove the left-hand side is equal to the right-hand side when we have a certain identity. Okay? So let me show you what I mean by that. We'll start with simplifying expressions involving trig functions. Okay, so let's say I'm asked to simplify each of the following to an expression involving a single trig function with no fractions. So to an expression, let me fix that. Involving a single trigonometric function and I don't want fractions. I just want the answer in the numerator, right, with no fractions. Okay, so the first problem is this. So I'm given cosecant of, instead of theta, I'm just going to use t here for my angle, and then tan times tan of t. So I want to simplify that to a single trig function with no fractions. So one way of doing this, and I think maybe this is probably the best approach, is first rewrite everything in terms of sines and cosines, and then simplify, use algebra to simplify what you have left over in terms of sines and cosines. So we know that cosecant is the same as 1 over sine, so this is 1 over sine of t. And we know tangent is sine divided by cosine, right? So it's sine of t divided by cosine of t. Now look what happens. I can cancel sine of t over sine of t, right? I'm assuming sine of t is not equal to 0. So I can cancel that. And what I have left is 1 over cosine of t. But what is 1 over cosine? That is secant. So this is equal to secant of t. And that's what I wanted, right? I wanted an answer with no fractions. So cosecant of t times tan of t is the same as secant of t. Okay, here's another example. Let's say I start with secant of t minus cosine of t over sine of t. Okay, so again, I'm going to write everything in terms of sines and cosines. So secant of t is 1 over cosine. And everything else is fine, right? Everything else is in terms of sines and cosines. Now, to simplify this, there's a couple of ways you could do this, but usually if you have like a rational expression like this and it has a bunch of denominators, usually what you do to simplify it is you multiply the numerator and denominator of that rational expression by the lowest common denominator. And look at all my denominators. I have cosine of t. This is like over 1. This is over 1. So really my LCD, my lowest common denominator, is cosine of t. So I can multiply the top by cosine of t and I can multiply the bottom by cosine of t. Why am I able to do that? Because what is cosine of t over cosine of t? That's 1, right? So I'm not changing the expression. I'm just rewriting it by multiplying this out. Okay, so let's do this. So if I distribute in cosine of t times 1 over cosine of t, that's just equal to 1. Cosine of t times minus cosine of t is minus cosine squared of t. And then in the bottom I have cosine of t times sine of t, right? You can't really do much more than that. Okay, but what is 1 minus cosine squared of t? Isn't that the same as sine squared of t, right? By using the Pythagorean identity. So remember, the Pythagorean identity says cosine squared plus sine squared is equal to 1. So if I were to subtract cosine squared from both sides, then I have sine squared is equal to 1 minus cosine squared, right? So that numerator is really just sine squared. So I have sine squared of t. The angle is going to be t in our case, t, divided by cosine of t, sine of t. Now, one of those signs can cancel, right? You can think of sine, if you want, you can think of sine t as sine squared of t as sine t times sine t. So then we can see one of them cancels, right? Sometimes people just cancel the exponent on top, right? But that's what I mean. And then what's sine divided by cosine? That's tangent. So this is equal to tan of t. So the original expression, which was here, secant of t minus cosine of t divided by sine of t, ultimately when you work it all out, is just tan of t, right? Just the tangent of t. Okay, here's another one. Let's say we have 1 plus cotangent of t over 1 plus tan of t. And I want to simplify that and rewrite it so that it's just a single, some type of single trig function with no fractions at all. All right, so let me convert everything to sines and cosines. So remember, cotangent is 1 over tangent, but since tangent is sine over cosine, cotangent is cosine over sine, right? So this is going to be 1 plus cosine of t over sine of t over, and then tangent is sine of t over cosine of t. Now again, I have this complex rational expression. I want to simplify it. So I can do that if I multiply everything by the lowest common denominator. In this case, the lowest common denominator looks like it's going to be sine of t times cosine of t. So if I multiply the numerator by sine of t cosine of t, and then same thing in the denominator. And again, the reason why I can do that is I'm just really multiplying by a factor of 1. So I'm not changing anything. I'm just going to rewrite this expression. All right, so if I distribute this in, right, well, sine of t cosine of t times 1 is just sine of t cosine of t. And then sine of t cosine of t times cosine of t over sine of t. Well, the sine of t's are going to cancel, and it looks like I'm going to get cosine squared of t. And then in the denominator, right, if I distribute this in, I'm going to get sine of t cosine of t. And now it looks like the cosines are going to cancel. When I multiply by the second term, the cosines are going to cancel, and I'm going to get plus sine squared of t. Okay, what I could do now, looks like in the numerator, see how cosine is common? There's two, so there's at least one there and there's one there. It's common to both terms. So I could factor it out. And I'm left with sine of t plus cosine of t. Right? Because if I multiplied it back, I would get cosine sine or sine cosine plus cosine squared. So if I factor it out, I'm left with sine of t plus cosine of t. And it looks like in the denominator, I could factor out a sine of t. And I'm left with cosine of t plus sine of t. Well, look at what's going on here. You may not recognize this at first, but in parentheses, those are both the same terms, right? Because they're added. Sine plus cosine is the same as cosine plus sine. So I can cancel these. That's just equal to 1. And then what is cosine divided by sine? That is cotangent. Right? So this is going to be cotangent of t. And that's my answer. Right, so this 1 plus cotangent of t divided by 1 plus tan t turns out, when you work all this out, it's just equal to cotangent of t. Okay. Oh, here's a quick one. Let's do one more quick one here. Let's say I have this. Sine squared of t plus cosine squared of t divided by cosine squared of t. Now here, right, if you think about this, look at that numerator closely. Sine squared plus cosine squared. Well, that's the same as cosine squared plus sine squared. And we know, based on the Pythagorean identity, that's equal to 1, right? The numerator is just 1. And then what is 1 over cosine? 1 over cosine is secant, right? But you can think of this, if you want, you can think of this as 1 over cosine of t, but it's all squared, because 1 squared is 1. Cosine of t squared would be cosine squared of t. And 1 over cosine, again, is just secant. So then this answer is going to be equal to the secant squared of t. So that's it. So it was quick. Just you had to recognize that numerator was nothing more than 1, right, from the Pythagorean identity. Okay, now let's, for the last thing, and again, this is related to what I just did, let's prove some identities. We got to prove that both sides, expressions on both sides of an equal sign, both sides of the equation, are the same. Okay, so I want to prove some identities next. Okay, so again, what I want to do in this last little piece is I want to prove some identities. So prove the identities. And this is probably best explained by an example. So let me just start with an example. Let's say we're told that sine squared of theta, I'm using theta now instead of t, but you can use anything for your angle, right? So sine squared of theta plus or over 1 plus cosine of theta. Let's say we're told that that equals 1 minus cosine of theta. Okay, and we want to prove that that's true, that those are equal, right? It's an identity. For any replacement of the angle theta that makes sense, right, then that'll be true. The left-hand side will equal the right-hand side. So the way you typically go about this is you try and simplify the side that's more complicated to look like the side that's less complicated. So in this case, right, the left-hand side is more complicated. I mean, it looks more complicated. Sometimes it's not obvious, but it looks more complicated than the right-hand side. So let's try to make it look like the right-hand side. And if we can get the left-hand side to look like the right-hand side, then we know that it's true, right? But they both look exactly the same, then we've proved the identity. So let's try to make it look like the right-hand side. Okay, so, and this is not always easy to do. Sometimes you have to be creative. Sometimes I get stuck on these myself. I don't know exactly how to proceed, but I just try different things. And a lot of it just comes with practice, right? With experience, like anything else. You have to start doing a lot of these things and you'll see patterns and see things that have worked in the past, etc. So somehow I need to get that to look like 1 minus cosine. Well, since there's no signs at all in that right-hand side, I probably want to see if I can replace the sine squared with a bunch of cosines. Well, I do know a relationship, right? Remember the Pythagorean identity says that sine squared is 1 minus cosine squared. So I could replace the sine squared on top with 1 minus cosine squared of theta. That comes from Pythagorean identity, okay? Now here's something that, again, it may not be obvious, you may not recognize this. This kind of comes with experience. See how the numerator is like, it's like something squared, I'll call it a squared, minus something squared, minus b squared, right? Because 1 is 1 squared, cosine squared is cosine of theta squared. Well, that factors into a plus b times a minus b, right? If we were to FOIL this back out, you're going to find that you're just going to get a squared minus b squared. So it factors into a plus b times a minus b. Do you guys see that? So think of like 1 is like 1 squared, and then this is minus cosine of theta squared. So it's like a squared minus b squared, right? That we have that form on the left-hand side there. So what I can do is I can rewrite that numerator as 1 plus cosine of theta times 1 minus cosine theta. And in denominator, I have 1 plus cosine theta. Well, this is nice, right? Because now look what happens in the, look what I can do now. I can cancel the 1 plus cosine theta over 1 plus cosine theta. That's just 1. So I can cancel those. And what am I left with? I'm left with 1 minus cosine theta. And that's what we wanted to prove, right? That was exactly what we had. If you go back to the original question, that was on the right-hand side. So since the left-hand side is really equal to the right-hand side, I've proved that identity. Okay? So really that's like the gist of how you want to solve these. You want to look at the more complex side and try and get it to look like the opposite side, right? The side that's a little easier. All right, so here's another example. Let's say I have cosecant squared of, I'll call x my angle now, minus sine squared of x over cosecant of x plus sine of x. So that equals cosine of x times cotangent of x. We want to prove this, okay? So let's look at the left-hand side. I'm just going to focus on the left-hand side. Well, if you look at the left-hand side, again, the numerator, it looks like a squared minus b squared. So it looks like the numerator can be factored into a plus b. So it'd be cosecant of x plus sine of x times a cosecant of x minus b. So minus sine of x over, and then I have cosecant of x plus sine of x. Now again, this is nice because look what happens. These cancel, right? So I have cosecant of x minus sine of x. Well, it's still not equal to the right-hand side, but at least it's a little better now, right? But this, can I write this as, remember cosecant is 1 over sine? If I want to subtract those functions, or those fractions, then think of sine as sine over 1. Well, if I want to subtract them, I need to have the same denominator. So I can fix this one if I multiply by sine of x over sine of x. Then I'm going to have, in the numerator, I'm going to have 1 minus sine squared of x over sine of x, right? So I'm just subtracting fractions. I rewrote the sine of x as sine squared over sine, so then I could subtract them. But what is 1 minus sine squared? What is that numerator now? Isn't that just cosine squared? So this is equal to cosine squared of x over sine of x. Remember, ultimately we want to try and get this, right? This right-hand side, cosine times cotangent. Actually, it looks like we have it already, right? So we have to break this up a little bit. Instead of cosine squared, let me write this as cosine of x times, and then I'll write cosine of x over sine of x. Right? That's the same thing. I just broke it up in that way. But what is this term right here? What's cosine divided by sine? That's cotangent. So now this is cosine of x times cotangent of x. And that's exactly what we wanted to prove, right? We got exactly the right-hand side now. So again, there's no easy way of explaining how to do this. You have to just apply different rules and try different things until you get the more difficult side to look like the easier side, right? Or somehow get both sides to look the same. Okay, let me do one more example. Let's say we want to prove, oops, let me go back to black here. Let's say I want to prove that sine of theta minus cosine of theta over secant of theta minus cosecant of theta equals sine of theta times cosine of theta. So again, the left-hand side is definitely much more difficult. So I want to work on the left-hand side and see if I can make it to somehow do a bunch of things and make it look like the right-hand side, right? So my goal is to try and get the left-hand side to look like sine times cosine. Okay, so first of all, let me write everything in terms of sines and cosines. So the numerator is okay. The denominator, well, secant is 1 over cosine, and cosecant is 1 over sine. Okay, now I have this like complex sort of rational expression here. I can simplify it by multiplying both the numerator and denominator by the lowest common denominator, which these are really just over 1, right? Over 1. So it looks like it's cosine times sine is going to be my LCD. So I want to multiply the numerator by that. And I want to multiply the denominator by that. Okay, so normally I would distribute in the cosine sign into the numerator, but I'm going to hold off on that for a second and I'll show you why. So I'm just going to distribute this into the denominator. And again, this is not obvious. This is more just experience because I can kind of see where I'm heading. So I have cosine of theta sine of theta times sine of theta minus cosine of theta over, I'm just leaving the numerator alone. Now if I distribute this in, cosine of theta times sine of theta times 1 over cosine. Well, the cosines are going to cancel, right? I'm going to get sine of theta times 1, which is the sine of theta, minus, and then cosine of theta sine of theta times 1 over sine. The sines cancel, and I'm left with cosine of theta. Now look what happens. Since I didn't distribute that in, right, these cancel. And I'm left with cosine of theta times sine of theta. And that's exactly what we wanted to find, right? In fact, it's written the other way, but it doesn't. A times B is the same as B times A, right? This is the same as, doesn't matter what order I write these in. So this was exactly what I wanted to end up with, right? So I proved that identity. Great. Okay, so that's it for 5.4. Next, what I'll do is I'll do a little bit where I talk about the fact that the sine and cosine functions, and in really all the trig functions, but I'm just going to focus on sine and cosine and talk a little bit about this. The fact that they're periodic functions. I want to do a little bit with inverse functions, and then a little bit with vectors. And then that'll be it for the course. Okay, so a few more lectures. Great, thanks.